Okay, so now that we've looked at the axioms a little bit and defined the absolute value and all of that stuff, it's time to, so before we looked at the field axioms and the ordering axioms, but there was one other axiom, right, which was this completeness axiom. That's special to R, okay? And the completeness axiom in concert with the other ones really, it turns out to actually be enough to characterize R like uniquely, okay? So the completeness axiom is extremely important. Now, to get to that point, like to be able to phrase the completeness axiom, we have to define these concepts of Suprema and Infima. So that's what I'm going to do first. But I want to give you a little bit of a preview of like why we're doing it this way. Why are Suprema and Infima so important? Why, or Suprema really are enough on their own, actually. So why are Suprema, aka least upper bounds, why is that important? And how is it related to completeness, right? If you go back, if you think back to like where we kind of started the discussion, we started with the natural numbers and then we looked at Q, right? And I was pointing out along the way that, you know, each of these number systems was missing certain numbers, right? So Q and other earlier number systems are missing numbers. Okay, like pi and e and so on, right? And sometimes like the way we tried to get from one number system to the next to like improve it would just be to add more numbers in, right? Like, so we can create the algebraic numbers just by kind of adding in all the square roots and all the cube roots and everything, just like throw them all in there, and then you get a new number system, right? But the thing is about that, like you can actually describe all those numbers. All the algebraic numbers you can actually write down with like a finite expression. But there are a lot of real numbers that you just can't write down at all. There are too many of them, basically, right? So how could you actually build the real number system? Like how can you be sure once you've added like all the numbers that you need, right? All the numbers that could possibly exist. One approach to this would just be to use like decimal expansions or something and say like, well, all the possible decimal expansions, infinite decimal expansions are valid, plus, you know, sometimes they represent the same number or something. That's a very bad way of doing it. It could work, but it's bad and it will not be illuminating. So this approach is much better and it's much more in the spirit of real analysis. But basically think about it this way. Each missing number, so each missing number is kind of like a gap. So they have gaps in the number line, right? Like square root of 2 was a gap in Q. So the big insight here is that every gap, let's focus on Q. So every gap in Q is, can be found with a subset whose so which doesn't have a least upper bound. So for example, oops. This set of Q, all the rational numbers for which Q squared is less than or equal to 2 has no least upper bound. And I know I haven't defined a least upper bound, but hopefully it's kind of intuitive from looking at this that that basically the least upper bound of this set in the real numbers, it should be the square root of 2, right? This is just some subset of the rational numbers, but basically it sort of fades off in the rational numbers and there's no specific rational number, which is kind of the boundary point of this set, okay? Because the square root of 2 is just missing, right? So that's an example of a number that's missing, and you can detect it by kind of forming a set whose least upper bound is supposed to be that number, right? So actually every missing number is in a sort of abstract, sort of philosophical way, every missing number in Q that should be in R, right? Every one of those missing numbers is the least upper bound of some weird subset of Q. So in principle, you could build the real number system by basically going through all of the subsets of Q, figuring out what their least upper bound should be, and if it's missing, just introduce that as a new number, basically, okay? But obviously, that's kind of an abstract process. We're gonna avoid doing that. That's kind of what Dedekind cuts do, actually. So section 6 of chapter 1 is about Dedekind cuts, and that's one way of describing this process of introducing all these least upper bounds. But what we're gonna do is we're just gonna declare that every subset will have a least upper bound, and that's gonna be enough to, and we'll just sort of assume that the real numbers are a system with that property, and that will be enough for us, okay? So with that out of the way, so this is called the Suprema, right? So anyway, so to work towards that, we have to define what least upper bounds and maxima and minima, least upper bounds, greatest lower bounds for sets and stuff like that. So let's start with the really simple ones. So maxima and minima. So I'm gonna clear this. So maxima and minima. This is a very straightforward idea. So they define it for any subset of R, which I'm going to do too, just to be consistent, although I understand if it feels strange since, again, we haven't really defined R, but you can restrict these definitions to Q, and then you can use these definitions to build R, like I was saying, if you want. So, so S is a subset of R if S has a greatest element. So that is some element little s for which t is less than or equal to little s for all t in S. So it's just literally bigger than every other element of S, or equal, obviously, since it's in the set. Then we call that max S. That's the notation. And similarly, if S has a least element, call that min S. Seems simple enough. Now, the thing about this is that even in R, there are lots of subsets that do not have maxima and minima, all right? So I'll show you some examples. Couple examples. So finite subsets always have maxima and minima, right? Like the max of 1, 2, 3 is 3. Dang it. 3s are hard to write in this. And the min is 1, obviously. Intervals. So I'll explain a little bit of notation here. So I'll just write some of this stuff. So max A, B equals B, min A, B equals A, max A, B does not exist, min A, B equals A, and you can kind of fill in the blanks yourself for the rest of them. So basically, what this notation, which I kind of mentioned earlier too, this represents a set, okay, in our little world here. This represents the set of all numbers in between A and B, including A and B, okay? So that would be like, well, I'm not gonna write it down in full, but you can find the definition in the textbook if you want on page 20. So this is everything in between A and B, including A and B, but that's because it's square brackets, right? So if you replace one of those square brackets with like a curve with a parenthesis, right, then that means you exclude that endpoint. So in this case, we include the endpoint A on the segment and we exclude the endpoint B. A common interval or a common visualization of this is like with an empty circle. So this would be like including both, right? And this is excluding this one. So that's why this one still has a min, but it does not have a max, okay? Yeah, and you should really think about, don't like just gloss over the fact that the maximum of this doesn't exist. Think about it, right? If you pick any point in this set, you can always go a little bit further towards this endpoint to get a bigger one. So that's why there's no max, okay? And then lastly, there are some unbounded subsets. So like Z and Q have no max or min. And that's because the elements of Z and Q just get really, really big and really, really small. I mean, they go towards positive and negative infinity. There's no end to them. So they don't have maxes or mins for that reason, right? It like take note of the fact that in this case, in the second case up here, these sets are actually bounded. They don't extend infinitely, but they still don't have maxes or mins sometimes, right? If they're just missing these endpoints. This is kind of a more obvious one down here, that the max and the min don't exist because the sets are just infinite, or they just go infinitely far. I mean, these are infinite sets too, in that they have infinitely many elements. So, okay, now that we've defined max and min, let's define boundedness, right? Good. So I'm gonna erase this part up here. So boundedness is going to be another so max and min actually, like, they're not super important. They're not super important terms. One nice thing about defining them here is just that they illustrate some contrast with supremum and infimum, which are different, very different concepts from max and min. They're sort of related, but they're still really, you have to treat them very differently. But max and min on their own, like, are not, we don't use it a ton. It's just kind of a convenient notation, really. So let's see. Now boundedness. So if S is a subset of R, and let's say, right, M is a number with, S less than or equal to M for all S in S, then we call M an upper bound of S, okay? And similarly, oh, sorry, before I do that, in this case, if, so any upper bound exists, we say S is bounded above. Important terms, very important terms. And then similarly for lower bounds and bounded below. Right, so just to return to these examples, I won't really write anything here, but you know, in the first two bullet points, all the sets are bounded. So if we just say the word bounded, so, sorry, bounded above and below, we just call that bounded. So if we say a set is bounded with no other qualifiers, that implies it's bounded both above and below, okay? But if it's just bounded in one direction, we don't call it a bounded set. So these sets are bounded actually in both directions. So they're just bounded, right? 1, 2, 3 is bounded, obviously. An example of an upper bound for 1, 2, 3 would be 4. That's an upper bound of the set. 17 is also an upper bound of the set. You know, a googolplex is an upper bound of the set. 3 is also an upper bound of the set. So if a set has a maximum element, that maximum element serves as an upper bound, right? And similarly with minimum. So, you know, the minimum, like 1 would be a lower bound for these sets, or this set, right? Or -1, negative like a million or whatever, right? Those are all bounds, valid bounds. Similarly here, you know, A, B, any number bigger than B is an upper bound. Any number smaller than A is a lower bound. You get the picture, right? Same thing here. Any number bigger than B. B is still an upper bound of this set, even though it's not in the set, right? It's still an upper bound. And then obviously here, Z and Q are unbounded in both directions. So they're neither bounded above nor bounded below. There are no upper or lower bounds. So that's that. Let's move on to the next thing. I think with that, we can just define supremum and infimum, and then call it quits for this segment here. Although there will be more lecture after this. So supremum and infimum, right? So, right. So if S is a subset of R, let's say, well, okay, the way they phrase it in the book, I'll use their phrasing and then I'll kind of explain it. So if S has a least upper bound, then call that the supremum of S, which we write as sup S. And similarly, if S has a greatest lower bound, call that the infimum, which is inf S, okay? So when they say least upper bound, to make that super precise and rigorous, unambiguous in terms of everything we've done so far, the real way you'd phrase it would be that to say, oh, my pad seems to have stopped working. Oh, there we go. The real way to phrase that would be to say, if you look at the set of all upper bounds of S, if that set has a minimum, right, then call that the supremum. Because we already defined upper bounds and we defined what it means to be the minimum of a set. So what we're saying is, if you take the set of all upper bounds of S, and that has a minimum element, we call that the supremum of S. And similarly, if you look at all the lower bounds of S, then that, and if that set has a maximum, call that the infimum, okay? So let's look at the examples one more time. The supremum, what do you think the supremum of this set would be? Pause for a sec maybe and think. So the answer is 3. The supremum is 3. And actually, as a general rule, anytime a set has a maximum element, that is also going to be the supremum, okay? If it has a maximum, that's the supremum. Similarly, the infimum is 1 because it has a minimum, and that's 1. Now, with the intervals, let's look at the closed interval. What do you think the supremum would be here? So if you said it's B, you'd be right, because what I just said applies here too, right? It has a maximum element. So now here, you can probably guess that the supremum should be B again, even though it's not in the set. That's the key about Suprema, is that they're sort of like maxima, quote unquote, but they don't always have to be in the set, okay? It seems simple, but this is actually a very subtle idea. So yeah, the supremum of this interval, half open interval, is B, the infimum is A, and Z and Q currently have no supremum or infimum. I'll say this is currently because we're going to actually sort of define the symbols plus and minus infinity, and we will be using those just as shorthand basically, but those are sort of artificial. They're not actually numbers. They just stand for saying things are like not bounded above or not bounded below. So the last little thing I want to do here is, I'm just going to clear everything, give you a lecture question. So lecture 2, question 1. What are the supremum and infimum of the set 1 over n for n in the natural numbers? So please take a bit of time and write your answer down to the best of your ability in your own words. And now I will answer it, or after you pause. So the answer here is the supremum is 1. It can be helpful in these situations to try to visualize the set on the number line, right? So we're just taking all the integers and then doing 1 over that. So, right, it gets small, this number gets smaller and smaller the bigger n gets, right? So the biggest number that's going to be in here is just when n is as small as possible, which is when n is 1. So here's 1, right? Then 1/2 is going to be in it, 1/3 is going to be in it, 1/4, and so on. And then it just gets like, you know, goes infinitely, gets infinitely close to 0, right? But 0 is not in the set. But anyway, so you can see from here that obviously, you know, there's nothing bigger than 1. It's just the maximum. So that's also the supremum. So in this case, it's also the maximum. The infimum, as you can tell from this picture, is 0, but there's no minimum, right? Because these numbers just keep getting smaller and they never stop. And 0 is not in the set. So there's no minimum, just an infimum. And that does it for this video. So I'll see you in the next part.